Hello, I'm Michał, and I will have a short presentation about the optical key distribution and the different strategies of eavesdropping in this protocol. So, something. Oh, okay. I study formally in Warsaw, and this project I joined before coming here to Palermo. It's a group, it's the Center for Quantum Optical Technologies, and the head of the group is Professor Konrad Benaszek. Maybe some of you know him. And I chose to talk about this because I think that this is a bit of a different topic than you usually do here in Palermo. So maybe it will be something new for you. So just a very quick reminder about the quantum key distribution. I'm not gonna go into details because I guess everybody knows more than me about it. And also we had a seminar by Sujan about this. So just to remind, we have two parties. We have Alice and Bob. They want to communicate a secret key between them, which can later be used in some cryptographic protocols. And to do that, they use the properties of quantum mechanics. They send qubits, they use different bases, non-orthogonal bases, which then provide some uncertainty in the measurements. And because of that, security emerges in this protocol. And what we usually add is an eavesdropper who tries to get to know the secure key. And yeah, this is a pretty old task in quantum cryptography and communications to see what is the amount of secure key that can be sent from Alice to Bob. When we assume that there are some imperfections of the transmission and that are usually given as the quantum bit error rate, if I remember correctly, the QBER. Yeah. I'm just saying about this because there are some similarities in the protocol that I will be showing, the optical key distribution. So I thought it's good to just give a short reminder about the QKD. So the optical key distribution, the task is the same. We have two parties that want to exchange the secure key channel. And the difference is that here we are in a little bit more realistic scenario, and what Alice is using to send the bits, encrypt the bits, is laser pulses, some bunches of photons that can be described as coherent states. And yes, Alice encodes bits using coherent states, and what is binary modulation I will show in a bit on the picture. And we assume that in every scenario of communication, Bob decodes the message using just a simple photon counter. So from the coherent state, he can only measure the amplitude. And Eve has access to some more advanced technologies, and I will be talking about this later in the presentation. The idea is that Eve is better equipped than Bob, and we see how much Alice and Bob can transmit between each other. So this is the scheme, more or less. We have Alice that, depending on which bit she wants to send, 0 or 1, she will send a coherent state with an amplitude of n0 or n1. And then, and in this case, both Bob and Eve are shown to receive a sort of a Gaussian state. It's because we assume that there is some shot noise of detection in the devices of Bob and Eve. And important thing is that the transmission of the signal is lossy. So just a fraction tau b of the signal reaches Bob, and accordingly the fraction tau b reaches Eve. and they don't need to sum up to 1. So we can also assume that there is some loss of the photons of the signal that just disappears somewhere. And an important quantity that will be used later in the presentation is this epsilon, which we call the eavesdropper's advantage. And when you look at it, it's pretty obvious why, because this tells you how much more signal reaches Eve than Bob. And as in the quantum key distribution, the security and the uncertainties came from the anorthogonality of the bases of like the sender and the receiver. Here it's coming from the overlap of the received Gaussian states, both for Bob and for Eve. And as in the case of QKD, we again measure the quality of the transmission with the secure key rate. And earlier it was a function of the Q-bar, the error rate. Here it's going to be a function of this, of the eavesdropper's advantage. So, yes.
I didn't really understood how you mix using Korean states, like cat states, we have like amplitude of amplitude minus amplitude.
I mean, when Alice wants to send a bit, for example, the bit 0, yes, she will send a coherent state with a given amplitude, like just some number. And when she wants to send a different one, it's going to be one with a higher amplitude. And is it?
Typically, it's perfectly right. But typically, so if alpha is larger than 1, so the amplitude of a coherent state is larger than 1, then the overlap between alpha minus alpha is e to power minus 2 alpha square modulus. Okay, right? So something of the order of 2 becomes already e to power minus 8. Okay, so the overlap is very small. So the usual rule is in alpha minus alpha. And then you are right, if I want to send a cube rather than a piece, then I will need to alpha plus or minus, so minus alpha. So arbitrary states. So unique so there are already there are frameworks of computation, quantum computing with this sort of where the typical infinity which we collect from the gates are relaxed. But where the problem is that the reliable. Because I should be account of sufficiently large amplitude in this transaction.
Follow-up question why the overlap is a measure of use? Why have overlap?
You need them to be distinguished.
So yeah, that's why overlap is if I see overlap, I should get used to it rather than kind of overlap
But again, I mean, this will not be a measure of security. This is just some variable, like some parameter of the scenario that we have. And then from this, in different cases of what type of detection if it's going to perform, like we will only then, using this formula, calculate what is the key amount. So, okay, this is something that characterizes the specific situation that we have, and then from that we will see how secure it is by calculating the mutual information set the key amount. Fine? Okay, good. So our point of departure, let's say, was a publication from 2021 by the group, in which they investigated a pretty simple scenario of when both Bob and Eve had access only to a photon counter, so they could just measure the amplitude of the coherent states, let's say. And so in this case, Eve had no technological advantage over Bob. And what they did, they derived some analytic formulas for key amounts. And what they got is that, because it was not so obvious, but that the key amounts depend only on the ratio of the fractions of signal reaching even pop, so the Eavesdropper's advantage, and not on the individual values of them. So we have something like this. It's written that it's approximate, but it's a very good approximation of the quantity. And I won't be getting into details here, but it's shown on the graph, so I will say about this. These two lower lines are for the binary modulation that I was mentioning earlier. And the one on the top is the theoretical limit for the amount of key that could be sent between Alice and Bob with this setup with sending photon pulses and having Bob count how many photons he receives. It happens when Alice, for the probability distribution, the photon number distribution that she sends is a Gaussian, and don't ask me why, please. But yeah, this is just a reference value for how good we can get with our transmission. And in some asymptotic limit of the noise that Eve experiences, like this is the formula for this upper limit. Okay. Just as an example, how you calculate those key amounts, you start from a tripartite probability distribution, you calculate the entropies, and the first one is easy, the second one is not that easy. So what they did, they just approximated the logarithm here as a Taylor series to the second order, and some integrals later we got that. What needs to be done here is this thing here needs to be optimized over the delta E. Hidden are some like variable changes that I won't be going into because it doesn't make sense. But this thing in front needs to be maximized in order to have the biggest possible key amount. And when you do it, it turns out to be around 1/2. And what's interesting is that what we got is just the optimal thing that I was talking about in the previous slides, rescaled by a factor of 1/2. So with their formula, they went on to apply it to some real world case. It was a low Earth orbit satellite communicating with a ground station, just like that. And I'm putting what they put in the paper, but I'm not really that familiar with how satellites work, so I will just report what they said. That during one pass over the orbit, they got a security rate of around 2.8 megabits per second, and from what I checked with some previous numbers, it's quite good. So they were happy with the result. Okay, so that was the work from 2021, and what me and another friend from the group did was to check some new measurements for each and how they perform. And we did the homodyne detection, the optimal Hellstrom measurement, an ambiguous Hellstrom measurement, and a collective measurement that saturates the Holeva bound for the mutual information between Bob and Eve. And yeah, that's just some homodyne. Numeric stuff and analytic formulas were derived for every case, and I will show them to you in a second. That's just a very quick slide. We did use some Python, some Mathematica for the ugly formulas, and for optimizing the things that we had to optimize. And just to show an example, one of the four, for example, with the optimal Hellstrom for distinguishing between two non-orthogonal states, the error probability you probably, that's what it looked like for our coherent states with binary modulation, so with the different amplitude sent by Alice, the conditional probability distribution of like what Eve can detect depending on what Alice was sending, things like that. Then after some other integrals, we get to this formula. And again, this is simply something dependent on the delta E times a numerical factor times 1 over E. So again, we see the same expression that we saw before. When you optimize this thing, you get 1 over E times the Gaussian key amount. Again, it's quite interesting for me that it pops up all the time. And I didn't put the transitions here, but okay. So yes, so comparing all of the scenarios that we did, what's on the graph? We have on the x-axis, it's a bit cut off, but on the x-axis there's the eavesdropper's advantage, epsilon. On the y-axis there's the logarithm of the key rate, the secure key rate. And what we see a pretty logical thing that when Eve has more information than Bob, then the amount of secure key rate drops. This is logical, but the colorful lines are the ones that we added. I mean, in the new scenarios. So just to remind you, this black line and this gray, what do you call it when it's a line and a dot?
Dot dash.
Dot dash. The dot dash line were present already in the previous work. And we added the green, the purple, and the red one. So it turns out that okay, so the behavior is similar for all cases, which was already seen in the formulas because everything was just a rescaled version of the optimal one. But what we did was we actually got new lower and upper bounds for the key rates. And they, like the lower one, for me makes sense because it's the high-level measurement for Eve. So this is the theoretical limit of how good she can listen to Bob. But the one on the top, the green one, is almost coinciding with the for Eve performing an unambiguous Hellstrom measurement. And this, honestly, I am still not understanding that much why it performs so badly for her. But yeah, that's something to look at later. Okay, and as some next steps, we're thinking about some strategies to make it more difficult for Eve to eavesdrop. One of this, in case, at least for her performing the homodyne detection, was to maybe randomize the phase of the state that we're sending. So we're not only sending using the amplitude of the coherent state, but also the full second degree of freedom with the phases. It was suggested to us that maybe we could use some new detection methods as the weak field homodyne. And when we have that, and we think that it's enough, maybe it could also be used to redo the same thing that they did with the satellite case and calculate how it would perform for some real-world scenario. And thank you. Yeah. I said it's short, so I will try to answer.
Yeah,
what was it?
One question, sorry.
Yes,
I didn't quite catch.
Yes.
So, how the different methods you mentioned for discrimination enter into the protocol?
And Pointer to the what? To the...
Like, so are these different ways to process the information, the measurement information to decide how to discriminate between the states, or are these entirely different measurement schemes you mentioned? Vision detection schemes, are there actually different physical schemes, or different ways of using the same scheme? Because, for example, from an arm sense, in my mind, it would be the same measurement space, but different.
I mean, okay, so...
how do you implement this?
How do we implement this?
Yeah, I would like to.
I mean, okay, so what happens in every scenario is that, at least that's how I imagine it, like we have, like, theoretically, we describe it as if sending one by one a coherent state with either an amplitude of, I think, the square root of n0 and square root of n1, so after you square them, you get the number of photons, which is n0 over n1. And then because of the losses and of the tau e and tau b fractions that I was mentioning that reach Bob and Eve, like the states that reach them have different amplitudes. Yeah.
So which of these schemes are you prepared now? All of them, or this is just a physical process?
Like all of them, yes. And then,
okay.
So like what reaches each, depending on what Alice was sending, is like the coherent state with an amplitude rescaled by the square root of tau e times the square root of the thing that Alice was sending. And yeah,
all this is very clear. What I guess the question is these 4 bullet points.
Yes.
Do they mean you have different detection methods?
Yes.
Each, or is different post-processing?
Different detection methods for each.
Okay. So
yes.
how would an optical Eavesdropping detector look like?
No, please don't ask me. We wanted to like check different available, like theoretically methods, like also the Halevo measurement. Like it's not something that like we need some, from what I understand, some quantum memory to do with, some collective measurement. So it's not.
No, but it's enough. Right?
Yeah.
There are 4 different detectors, so to say,
Yeah, that was the idea.
So each of them corresponds to different measurement schemes and/or ways to process information, I guess. And in each case, you have a way to decide when the states received are same or not. Yes, that is the protocol.
Like, yeah, I mean, for example, what I was showing in the next slide, like in the Eavesdropping measurement, you just are given the formula for what will be your error of distinguishing between the 2 states that you want. And from this, we build the probability distribution, and from this, we get the mutual information and get the key amount. That's the idea with every of the 4 schemes that we had. Something else? Something more? Okay, so thank you.